Yeah, also welcome from my side. Hello, everybody. My name is Thomas Schmidt. I'm also one of these, like Matthias, one of these RIOT grannies. I'm from Hamburg, Highway Hamburg. And it's my pleasure to moderate the keynote speech. And the keynote speech is given by Kulau, who is in a double position. He's at the one hand, on the one hand, he is a junior professor in the TU Hamburg. So that's actually builds a second strong leg in Hamburg for the RIOT community. And I hope we will intensify the cooperation. And he's also the head of development of DSI Aerospace. And that already tells us that he is involved in something which is outer space. And he will talk about more about this. Wearables for space. What I should emphasize, so at the TU Hamburg, he's the head of the Smart Sensors Group. What I also should emphasize, he's well known to the community. He did his PhD in TU Braunschweig with Lars Wolf, and is, I guess, famous for your overclocking, right? There is this other project which I at least try to talk with into is take chicken to space. But you are still arguing that it's impossible because he's a great mentor of chicken. So let's welcome Ulf for his talk, Wearables in Space.
Yeah, and the first thing I will do is I destroy the entire setup because I have to change the laptop. Yeah, thanks for the nice introduction. And yes, there's obviously also a reason why we can send chicken to space. Chicken have no peristaltic. So maybe you don't know this, but it is like this, and therefore they would starve in space. With this, maybe I start with a topic where we are working closer to the mic. Okay. With this, I would like to start with a topic where we are working on since a couple of years already. And this topic is Wearables for Space. And why is it relevant? I will convince you that we have to have a deeper look into what can we do in order to prevent astronauts in future to have health issues in space with wearables. But this is not that easy. We cannot just directly use the stuff that we already know, maybe with Apple Watch or the Fitbit and all this stuff. Good. Before we talk about space, we have to talk about how to get there. So first, a bit of theory. So don't worry, I will not talk about too much about theory, but this is a really important equation that we can derive here, and it is the ideal rocket equation. So we start with a rocket. What we have here, do we have a presenter somewhere? No, what we have here. And so when we consider a short portion of time, so delta t, we have here always a short portion of mass which is ejected by the rocket, this delta m. And this is ejected with a velocity of u. That's one thing. So what we have here is an impulse. Well, this delta p. What we have here. So this impulse leads to a movement of the rocket in the other direction. So, and the movement in the other direction could also be given here as an impulse, where we have this delta v, so this change in the velocity times the remaining mass of the rocket. So then we also know here by this law of the conservation of the momentum that we can just make an equation out of it. It's equal. And then we just reorder the stuff here. We have delta v here, we have a velocity here, we have delta m here and m here. So we can just integrate the stuff over delta m and delta v. And in the end, all this is not really important. What is really important is this one, the lower right corner here that you see. This is the ideal rocket equation. And you might think, what has this to do with electronics and all the stuff that I want to talk to you? It has a lot to do with all the stuff that I try to convince you why this is important. We can just take a simple example and say, okay, what kind of velocity do we need to reach a certain orbit? So, and which is, we have here now a LEO orbit, 300 kilometers. So we need a velocity of our spacecraft of roughly 7,700 meters per second. So when we now have a rocket, and nowadays rockets also use a lot of hydrogen that they burn, we can also get here the velocity of this hydrogen that is getting out of the nozzle of our rocket. So then the next thing that we can do is we can just calculate, okay, what is then, when we start with the mass of the rocket, in the end, the remaining mass that I can get into this orbit. And that's what the idle rocket actuation gives us here. So without looking at the details, believe me or not, you can do it at home as well. So when we have here now this small example, only 70% of the mass of the rocket we can get into this orbit. And when we go into practice, this is even worse because we have the structure of the rocket, we have also the fraction of the atmosphere and all this stuff. So the real payload fraction, this is called the payload fraction of a nowadays rocket, for instance, if we have a Falcon 9, is 4%. So 4% of all the stuff that we put on a rocket can get actually to space. The rest is fuel, structure, all the stuff. So that means whenever we send something, it needs to be really lightweight. So this is also when somebody asks, build some shielding around all this stuff. And this is not always possible because you have the payload fraction. It's really expensive to get something to space. And you cannot argue. Now you can make it cheaper, you can make the process cheaper, you can reuse also here the boosters and all this stuff, but in the end, you're discussing is physics. So that's it. Okay, so keep in mind that we need a lightweight solution for all of the stuff that we are doing. Second challenge when we go to space is particle radiation. So we have particles everywhere. We have, for instance, a solar wind, electrons and protons coming from our sun, which is a more or less constant flux, which is just flowing particles coming from the sun. So electrons, protons here in this case, because our star is breathing helium. So therefore, we have here a moderate solar wind where we get some particles, but this is not our biggest issue. Bigger issues is, and maybe you heard about this as well before, is when you have this coronal mass ejections, which is just a solar flare. So we have an event which takes maybe a few minutes, and then during this event, a lot of particles are highly accelerated, and then they have a high energy that are blown out. And if they hit some of our electronics, we get really in trouble. But this is an event which is not, depends on the activity of the sun. Another big issue that is hidden here in the right corner. We have galactic cosmic rays, which means highly energetic particles coming from wherever. That could be some kind of supernova, some star explosion, some other events that happen in space that accelerate particles. That could be really heavy ions, so up to iron. That could be iron ions that get accelerated and sent into space. And when they hit our electronics, we have a big issue. So this is my favorite slide when I talk about this in front of students. And the question is, why do they never think about this stuff? Well, and it has something to do with this device here. And I don't know the age of the community here, but usually nowadays when I show this to students, they have no idea what it is. I hope you know it. Does somebody know it? Yeah, exactly. And what has it to do with this radiation effects that we have? Long story short, we are living on a big dynamo. So our Earth has a fluid iron core. The effect is amazing, right? We have a fluid iron core, and this is rotating, and this induces a lot of magnetic field around the Earth, and this is our protection shield against all these radiating particles that are going through the space, so that we can live here. So it's a really nice planet. No? So therefore, we should not destroy it, because this is something which you do not find on every planet. The Mars does not have such a magnetic field, for instance. So therefore, 95% is now coming from the magnetic, from the core, from the iron core of our Earth, from the rotating core. The rest, that just to let you know, is from oceans, for instance. So the ocean, there's also some kind of ions, so salty ions, and then therefore we have also here 5%. Anyhow, so we have a protection shield, which is pretty nice. But whenever we're going out of space, we are leaving this protection field. And then we get in trouble, and we have to take care what will happen to our electronics. Okay. Just, to let you know, so this is another big issue that we see. These are the Van Allen belts, so these are radiation belts. So we have the magnetic field, which protects us from outside. But the issue is also that it can accelerate particles. So there are trapped particles in this magnetic field, and then I guess everybody knows when you have some magnets holding them together, they pretty fast accelerate. And therefore, the same happens here. When you have particles and they are in the magnetic field, they are accelerated, and the radiation gets even worse here. However, when we have here a look on where we are usually in the LEO orbit, so here's the LEO orbit, roughly 400 kilometers, the ISS, this is not a big issue. Yeah, so, but whenever we are traveling far outside, we are passing by the Van Allen valves. So that's actually a worse event that can happen because highly energetic particles will hit our spacecraft. But when we also go outside the entire radiation belts here, then we have an issue because we are unprotected at all. Yeah, so when we go to Moon or to Mars, we are unprotected. And so we could ask the question, what can happen? So no worries. I will tell you just a few examples what can happen. Don't be scared. There will be also for each slide a small recap. The only thing you have to remember is the second slide. Keep that in mind. What can happen? One thing that can happen is a total ionizing dose. And this is an effect that you see on the CMOS technology. So you talk about software, I talk about hardware now. So what happens is you have here this isolation between the gate and the substrate of your semiconductor. So what happens is you have a charged particle, which is here passing by. And this leads to the effect that you have a split up between electrons and holes. So by collision, it can happen that you split up here now the silicon dioxide into electrons and then into holes. And this is a big issue. This is actually a big issue because when you have now here some voltage level here, some charge on the gate, what happens is that the electrons will pretty fast move to this gate, while the holes that are there, they are slowly dropping down to the surface layer between the silicon dioxide and the surface of the semiconductor. And as the surface is not perfect, they are just trapped. And long story short, the only thing that you have to know is they are trapped. This effect accumulates, and therefore what we see in the end is that the charge of the surface layer is increased, which means the threshold voltage of the entire transistor is reduced. And then in the end, what we have is a transistor that is always conductive or always off. So always on, always off. It's damaged. I promise you, the only thing that you have to remember is, so when we have particles over time, the only thing that we see here is, okay, we have a difference in the threshold voltage, and at a certain time, the device is permanently damaged. So that happens, depending on the amount of radiation that you're exposed to. That is one effect. Two more, and then it gets interesting. The single event upset is also a really important effect that we see, and it has more or less the same origin. We have a particle striking here our semiconductor, and what happens is now we are not have a look on the silicon dioxide, but on the substrate, on the semiconductor itself. So the particle strikes by, we have the ionization, so we split up in electrons and holes, and then we have the issue when we look maybe here on the drain, that there's also, again, some voltage levels, so some charge, and all the little electrons that are here are attracted to move in this one direction of the voltage on the drain. So which means we have a directed flow of charge. So in other words, a current. And this is exactly what happens here. So what we see is that we have here now some kind of induction of a current flow in our device. And this is a big issue when we talk about devices that are switching. So when we have a CMOS structure and we have a lot of transistors in this, and we have now a current flow, it can indicate that, you have now a switching transistor or, an off transistor in this case. So which means we have temporary bit flips. And this could lead to some temporary effects, for instance, that we say, okay, an SRAM cell or whatever we have on our device might change its state. Long story short, we have now information that we are processing our device, and due to this single event upsets, it can happen that, maybe we have a bit flip here in our information, and this, for you all know this, this propagates through the entire system. It might lead to a major malfunctioning of the system. So last but not least, then at least the theory is done, but it's important to understand this, are single event latch-ups. So what happens here is, we have to have a closer look again on the structure of CMOS. And I have to admit that, okay, there are also CMOS structures nowadays with technology nodes that are not really affected by this one, but it can still happen. And when you look at the structure, okay, we have field effect transistors, pretty nice. That's why we use them, because they're really efficient. We can scale them down, all the stuff. But what we also see here is that we have parasitic transistors which are forming in the substrate. We have N-doped material, P-doped material, And so what we in the end have is layers of NPN and PNP, and then you look back in the good old times of computer engineering and remember, this is a bipolar transistor. And this is exactly what we have here as a structure on the CMOS. So when we make, let's say an alternative diagram out of it, it's looked like this, and this one is a thyristor. What happens now? We go through this step by step. So we know when there's a charged particle, we can induce a current. So which means it can happen that we induce here a base current on transistor 1. Transistor 1 is now conductive, which means when this transistor here is conductive, we have also a current flow through this resistor, resistor 1. That means that we have also a current flow for the base current of transistor 2. And again, we have now a circle. And what is more important is we have a short on the semiconductor. So now we have VDD directly connected to our ground, which means we have a short. And this is exactly what happens. The stuff, well, it's not working. The stuff could burn by thermal issues. So, and this is what you can also have. And then the device is for sure also damaged permanently. So worst case scenario is we have a charged particle leading to such a latch up, and then the device is also burning away. That's it. Well, this is the stuff that you have to know in short when we are taking electronics to space. It's really hard to get something up there. It's really expensive. And the other thing is we have to deal with radiation effects on our device, which we have to somehow deal with. Now I make a switch to the stuff that we are doing because I want to talk about wearables. And this is the topic of this health monitoring. So this is a topic that is getting now a bit more important. So on ISS, as I showed you before, we are only a low Earth orbit, which there is an increased radiation, but radiation was never such a big issue for the astronauts and also not for, let's say, the gadgets that you have for monitoring the health condition of astronauts in this case. But now when we think about destinations like the moon or maybe also the Mars, which is happening, when not now, then maybe a few years later, then we have to take care about all these effects. And this is what we try to investigate in our research, that we say, okay, when we have the space environment, that also affects our astronauts. And the radiation affects the astronauts for sure, but also, and this is something where we can discuss also hours about, is the entire environment, like weightlessness and stuff. This is a nightmare for every human being. Now, at least we're not starving, like the chickens, but there are a lot of things happening which I do not want to explain here. I just can recommend you, there's a video from Arte, so it's in German and French. English, I don't know if there's a translation, but there you can also see there's a nice video what happens to the human body when you are in weightlessness, and this is a lot. So therefore, what we have to do is we have to find a solution where we can make a health monitoring for astronauts, which they can use on a daily basis, which is really lightweight. And that's where we come to the point, okay, we need wearables that are capable in this environment to measure a comprehensive picture of the human being, in this case, what we are focusing on, the cardiovascular system. So remember all the stuff, it needs to be small, it needs to be also really, really reliable, and therefore this is something what we want to do. Okay, the method that we want to investigate, or that we are investigating here in this case, is the so-called seismocardiogram. So this is also this is something we are investigating this because this is on its own an entire research topic. So the idea is pretty dumb and pretty simple. And there are papers going back 200 years ago where they investigated, okay, we have a heart which is moving, and the ballistic force of the heart is leading to the effect that we are shifting the center of the gravity of the human body. So you can notice this when you maybe, I don't know, by just putting your hand on your chest, you directly know, okay, there's something going on in your body. So when there's something going on that you can feel, you can also measure it. And this is what we are doing here. We are measuring the heart's movement, which is propagated through the human body on the surface. Why are we doing this? Because it gives us a lot more insights into the physical movement of, in this case, the heart. So what we see is not just the heartbeat. What we see is not just here the systolic and diastolic area of the heart, but what we also see are all the tiny things going on during a heartbeat, like valve openings, closings, blood flow, like the rapid ejection, rapid refill, all the stuff we can see here in the signal, which gives us a much more information content about the health status, the cardiovascular health status of a person. But, actually, it's not that simple. But in order to talk about this, maybe we can do this during the coffee break, because there is a huge discussion in the community how these peaks actually reflect to which movement, and how you can also define a method where you can make it inter-individual. But this is something maybe during coffee break. So for us as engineers, let's say, it's more interesting to say, okay, how can we actually measure this stuff? And because we are talking about really tiny accelerations, so in the area of some milli and micro G. So there are some peaks that are really important in the micro G area. So which is typically when we're using MEMS sensors in the noise floor level. And so one thing that we started here was some prototype implementation. And we started here with an FPGA. Why an FPGA I can discuss also later. And the idea here was we want to firstly improve here the signal quality. And what we are doing is we are applying here the method of differential sensing. We say, okay, we have two sensors in a differential orientation, and there are a lot of things going on the signal quality level. So we have a better linearization, usually of the unlinear behavior of the sensor units. But when you say, okay, the unlinearity is usually described as a Taylor series, and when you make a differential calculation, you can rule out here also at least the even terms, and therefore it's a bit more linear. But what is also more important is we have a much lower noise floor. So this goes back to the oversampling theorem. And so here we can say, and also we investigated that, there's 2 times higher SNR that we can gain by just using 2 sensors in differential orientation. And that helps us in order to lower the noise floor of the signal to get to such a nice signal here of the SCG later on. But there's for sure more. So when we talk about space applications, this also helps for redundancy reasons. So one thing is fault tolerance. So when we talk about the mean time to failure, we can increase here the mean time to failure by just using 2 sensors. The other thing is when we have this differential orientation, we can also rule out that we have common mode interference, which might happen due to radiation. So we have particles striking, and then we have maybe an effect that affects both sensors at the same. And by using the differential sensing, we can just cancel out this common mode interference, which is really effective. On the downside, we need special hardware. So therefore, we use here FPGAs. And for sure, the energy efficiency I don't talk about. So therefore, we just keep it as it is right now. So what we did was, so we had a first experiment on the ISS with this device. And the idea here was first to apply here this differential sensing for SCG signals on an astronaut in 0 gravity. The second question that we had here was also, because it's more for the medical guys, how do these signals change over time? Now for a monthly period that we say, okay, for 6 months on ISS, how does the signal change over time, which is also really important for them to know. Because when we are projecting this one to long-term missions, where we're talking about years, this is really important to know how does these change over time. Because there's a lot going on. So just as an example, when you have the heart, and I guess all of you saw the pictures when people are in weightlessness and then they have some kind of water bulb and then it's a nice little bulb forming. It's the same what happens with you in 0 gravity with your organs. So it's also forming a bulb. So the entire shape and the structure of your organs are changing, and therefore it's interesting to see how this mechanical movement is actually changing. Then there's another topic where I can also talk hours about is how is the signal formation actually taking place of this SCG signal, which is also a really important topic to understand how this actually forms in order to calculate back So ask me about this one in the coffee break. There's a lot of things right now also in a research project going on in order to face how is the signal actually formed and how can we calculate back to the actual HUDs, indicators that we have internal, like valves and stuff. Good. We had good luck, or great luck here. We have one male and one female astronaut, Matthias Maurer and Samantha Cristoforetti from Italy. And both were equipped with the sensors, and we collected a lot of data. The setup here that you see is pretty simple. We had just an FPGA implementing here these differential sensing approach, and then we have a communication module with an ultra-wideband radio, the good old decawave. I guess most of you maybe know this device. Why ultra-wideband? We can also maybe in the coffee break talk about this one. But the idea was here having a wireless sensor node on ISS in order to monitor here the cardiac movement of the astronaut. I cannot show too much, but more important, well, maybe I can show you the video. More important for us is, okay, this here on the left side, you see the setup, which was sent up there. So really bulky setup, to be honest. This is not a wearable, but okay, it's a first prototype, and therefore, it's like, it was qualified therefore, and okay, there's a lot of things going on. Why is it such bulky? And then for us, really important was to investigate also this common mode interference, which you see here on the lower left corner. So it's hard to see maybe on the screen here, but here you see there is some common mode interference on sensor A, the same here on sensor B, and for sure when we do the differential calculation, then it is more or less, almost, let's say here, cancelled out. So this is really important for us to understand, okay, we can cover here such events like SEUs and stuff when there's something happening on both sensors or maybe on the power line. Good. The stuff itself is working and running fine. The issue that I have is I cannot show you too much details about the cardiac stuff because this is something that we always have to ask ESA in order to show something from the astronauts' health data. But again, in the coffee break, maybe we can talk about this. Good. You saw that we can have sensors where we can have a comprehensive heart monitoring of astronauts. And the next step that we had was, okay, that was ISS, and ISS in terms of radiation effects is kindergarten. So this is not our goal. Our goal is to build a device which can go also beyond into deep space missions. And therefore, it needs to be smaller, much smaller, and it needs to be also radiation tolerant. So, and this is a goal that we are now investigating in the project SpacePatch. Something like this, the Star Trek fans of you know, this device here. Our shape of our device is also similar. It looks like this. And now finally there's RIOT. So now there's finally RIOT on this device. And why? And we choose RIOT here. I can also briefly explain, but first maybe about the hardware. The hardware itself is a highly integrated sensor where we have all the different stuff directly on board. So this differential sensing that we have here. We have an FPGA, and the FPGA is really important when we talk about radiation effects, because an FPGA is a device, even if it is not a space qualified device, what we can always do is we can integrate redundancy mechanisms. So we can build in already some redundancy in order to protect it against SEUs, for instance. And this is why we have always this FPGA. Plus, we have it for sure for this differential sensing that we are performing here for the for these sensors here. Lightweight, 6 gram. Then we have a Bluetooth low energy SoC here, so which we use for sure maybe when we want to do some software processing and for wireless communication. For ISS missions, usually what you have is a mission tablet. So therefore, the idea is also to send data to the tablet. And therefore, we have also here BLE SoC. When I say, okay, this BLE SoC already or also supports this 802.15.4, then you know what kind of device I'm talking about. So a commercial device. And really important for us is also a 1 gigabit protected, ECC protected memory for local storage of data, because autonomy is a really big issue. So you do not rely on some permanent wireless connection to some edge device. So you also need to be able to have autonomous operation. When we talk about components and hardware, so all these are commercial components, and the reason is pretty simple, because when we talk about class 1 devices or radiation hard devices, they are not available in this area of high integration. So this is a big issue. So we have to go back to commercial devices, and the only thing that we can do is we can build up on heritage. So sometimes you know what kind of devices are even capable to use in space. So what we are also doing is radiation testing. So we know what are the effects that are happening on our devices here. And so you are assembling your device up to your best knowledge, let's say. So this is something that we did here. So the devices that we have here, for sure, they are radiation tolerant, not hard. But at least better than nothing, because we thought about it in advance. I'll talk about the other stuff later, about MAVWES, for instance, but maybe let's just move on. So our research is more or less manifold. So we are doing on this device, on this tiny device. There are a lot of people working on the device, obviously, although it's so small. So one group, or one part of my group, is researching here effects on the FPGA itself, because this is our secure instance. So when something happens, and the FPGA is actually one device where we can say, okay, we can implement, for instance, TMR, so triple redundancy mechanisms, in order to get back to a reliable state, or make a supervisor for the entire system. So therefore, we have here the FPGA. But we have another issue. Now, this FPGA, which you see here, this one is really tiny FPGA, and it does not offer us some debug interfaces. Usually what you do when you're talking about FPGAs in space, you're doing scrubbing. So permanently what you are doing, you are reading out the configuration compared to a golden memory, and when there's a bit flip, you can say, oh, I reprogram my device and I'm done. You cannot do this here. But what you can do is, and this is what we did here in this research, is we built some kind of test core that is implemented here on the FPGA, and the test core itself is built in a redundant way, so it's more or less tolerant against some of the SEUs that I've talked about before. And what we are doing is we are building a wrapper around different IP cores that we can implement here on the FPGA. So we have more or less a really flexible test automa that we can deploy here on the FPGA. So we can feed in here some inputs. We can then read also the outputs. And this is a method where we can then detect, because we know where our IP cores on our FPGA, then we can say, okay, at least there was an issue, and we can detect these radiation-related issues, and then we can react. The good thing is that we can couple this one here also with the Bluetooth sock. And therefore, we have here a fully integrated test automa for the entire FPGA infrastructure, while everything is protected here against radiation. The implementation that you see here on the right side, you see it's dual redundant. We have shadow registers here, and also the communication is using here a repetition coding, so that we also have the information protected against bit flips in this case. That is the most important point. Good. It's really lightweight. So for those of you who are working with FPGAs, the entire test core just uses 77 lookup tables, which is almost nothing in this case. So the overhead is pretty low in this case. And as radiation testing is always a bit difficult, we are using here the concept of undervolting. So we're just reducing the voltage, and we induce here the errors by undervolting, and we see that we can reliably detect here also issues, random issues that happen by this test method. We also did some radiation testing with this core. In this case, we went to a facility and we made some electron testing. So electrons, as you heard before, the flux from the sun, for instance. Don't care about too much the details here. So 6 mega electron volt electron beam. So roughly when you say, okay, 0.5 kilowatt per minute, and then we were sitting there the entire night and waiting that something is happening. The issue was that unexpectedly, this FPGA, with a commercial FPGA, was pretty robust. So we had to stop due to timing issues with 70 kilorad. And this, just to give you a number, this corresponds to 10 to 15 years in LEO orbit. So therefore, that's pretty okay. The only issue that we have is that this is only reflecting to the total ionizing dose. So we can, the dose rate, we can pretty sure estimate it now with the device here, but there's an upcoming proton test. Unfortunately, this is taking place in 2 weeks, so no results. But therefore, we are going for proton testing. And in proton testing, we have here a proton beam. And then here in the end, there you have the test device under test. And then you're just throwing some particles on the device and see where on your device something is going wrong. It's as simple as that. And then you make some calculations and you get the cross-section of the device. And then you can later on project this into different orbits and say, okay, what is the probability of having issues in the end? So, but we are waiting for the results and looking forward. A lot of work in order to prepare the test. But next time, I can tell you more about the results here, but proton testing is then for the SEUs. We want to see actually bit flips there. Good. Another topic, which is also important, is qualification. And this is what we already did, because whenever we are sending something on a rocket, you have to qualify the stuff. So you cannot just say, okay, I take my device, which I want to have in space. First, what you have to show is that, is it actually capable of going there, and does it harm something? I'll tell you something a bit about this on the upcoming slides. And for the SpacePatch, we already saw for our previous version, we were on ISS, so that qualification process was already done. But now for the SpacePatch, our first actual mission was the Morpheus rocket. So they are regularly from S-range in northern Sweden. There are regularly some, let's say, science rockets going a parabolic flight. Now, they're not going to orbit, but what they are doing is a parabolic flight. So they're up and just down, and then you have 6 to 9 minutes of zero gravity, which is really important for some of the experiments on board. And we had the chance here to have our SpacePatches here as a piggyback experiment for IOV. So IOV is in orbit validation. So we want to see if actually everything survives, because you never know what happens. So there are resonators, or there are resonators or other components like MEM structures. And when you have a rocket launch, a real rocket launch, something on the mechanical devices, like for a MEM structure, could also break down, although you tested it before. So therefore, it's really important to have this one tested previously. Again, there's RIOT. So the reason is pretty simple, because the guy who was working here on the rocket patch was Christopher, who is also here, there. And he is obviously working a lot of his RIOT. And therefore, we also put it here on our mission patch. It was already flown to space, at least for, I don't know, 6 minutes, 9 minutes? 7.5. 7.5, okay, something in between. So there have at least, a few minutes we were in space already with the SpacePatch, but let's see what will happen. So we had been on a height of 309 kilometers, and the experiment was pretty interesting. I said to you that I want to talk a bit about qualification, and here is a really, really, really simplistic flow chart of how you can qualify a device. And the first thing that you always have in mind is, can it burn? So this is the nightmare that can happen. So you have to show, okay, there's nothing, you have to fuses and blah, 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 all this stuff. So when the stuff can burn, or there is a chance of that this stuff can harm some other components, when you have batteries on it, batteries is the worst thing that you can do. But it's also a different topic. But when there's something like this, this is an absolutely no-go. So then directly you can say, okay, this is something that you can forget. For sure, at a certain time, everything can burn in the end, but not by some crappy design or something. The next thing is that you have to make an EMC test. So you go to a facility, make some measurements, for instance, for EMI, so the interference. And is it also suspected here by EM radiation? If both is If this is yes, and this is below the threshold, we can just go to a shaker test. And the shaker test is just a mechanical test that shows if something is happening to the device. But to be honest, they don't care about the functionality of the device. Well, nobody cares about the functionality. They are not interested. They don't care if something is working in space or not. They just want to see if there are some components maybe falling off, and then maybe leading to a damage in zero gravity, while there's maybe some kind of battery holder or something breaking off and then floating to some other experiment. So the only reason here for the qualification is so do not harm other components or other experiments. So when we do not have any damage and we also do not see any harmful resonance that can happen, then we are good to go. And then we can also put the stuff here. In this case, we put it on the Marforce rocket. You see here one segment of the rocket. And here, here, and here, and here, and there were some different, rocket patches, which were the space patches, mounted here on the segment of the rocket. And here you see the retrieval of the data, because for us it was interesting to see what is the behavior as everything is surviving. Actually, temperature-wise, we were much outside the specification during the re-entry phase. And for us it was also interesting to test the autonomous collection of data, because Christoph implemented here some method in order to make a fast collection in the flash memory. And everything worked well. There were no outages, so every patches worked fine. And without showing too much detail, so this is the entire flight. And here during this phase, you do not see it pretty well. Maybe here this is 1G, and here actually 0G. So therefore, here we had been in space with the devices, and we are now also analyzing here the data, because there's much more that we can gain out of this data, for instance, also for the calibration of the sensors. So there's a lot of things going on right now. Next time, maybe a bit more. Here's the entire team of the rocket. Here you can see again the patches mounted on the segment of this Marforce rocket. There's also your control PCB. And one thing, at least for this rocket, which is okay, for the biggest one not, is Stabilit. The most important part here is Stabilit glue, that you can also glue the stuff here, worked also pretty well. This is after the re-entry. They have to collect the rocket somewhere in the out of nowhere. So I go with a helicopter and just collect the entire rocket back. And then afterwards, the stress starts, and then you connect the devices to your laptop and see if everything is working fine. What else? It's a pretty nice environment. You see also a lot of northern lights there. And what is also pretty cute is you don't see it here directly, but when you look really close in the lower corner there's always a fox running around. This is also pretty cute. So I can just recommend, when you do something, apply for this. There's also always a student project, which is Rexus. So when you are a student group or something, you can apply for experiments. This is here funded by DLR, but there's also something in the European level, which is called Rexus. And if you have interest in this, then also let me know. Maybe I can get in touch with the people, you in touch with the people there. Good. Last but not least, we also qualified here this stuff not only for Marforce, but we have undergone some certified qualification process for ISS again, and for MIL standard. So MIL standard is a military standard for US missions. And again, the shaker test that you see here on the left side. So what you try to do is, okay, is something damaged or not damaged? Is there some harmful resonance or whatever? This is something that you find out here, but it's barely to see, but all the stuff here is below the threshold, so therefore we are fine here. And also here, the EMI test. For our device, so you see here the thresholds for MIL standard, and here is for ISS. And our device with the SpacePatch is much below that one, despite one fact, when we have our BLE. So here on the 2.4 gigahertz, we see that we are above the thresholds, and therefore what we have to do in order to use BLE. So on ISS is not a big deal. For MIL it gets a bit harder, but what we have to do is here for us to adapt the transmit power. And then we are also fine, we are below the threshold, and then we can use it also BLE on yeah, for instance, on ISS, or what would be our dream is on Artemis, because that is a goal to get our device on an Artemis mission. But as you know, I don't talk about that here. Good. Last but not least, then I'm actually done, and you are done with me, I show you here a short video of a demo that we also brought here. And this is not fake. So we have our SpacePatch. And the nice thing about the SpacePatch, now it's running. So this nice lady is now holding this stuff here on the chest. And directly what you can see is the SEG signal. And the SEG signal can also be then translated into the, in this case, pretty simple. We have the heartbeat and we have also heart rate reliability. So, and the nice thing compared to ECG, for instance, is you don't have to unclose yourself, but you can just put it also on top of your pullover and stuff, and you directly see here some, at least heart rate, reliability, the stuff directly. And yeah, we can try it out. So we have it with us. This is something that you can also play around with in the demo session, I guess. Good. Maybe I took a bit more minutes, but hope this is okay. I'm done. Many thanks to my team, because this is for sure also a big teamwork, and also our project partners that we have, at least for this one here. And yeah, we hope that in future we get also onto a mission where we can actually leave our radiation belts and go maybe to Moon, Mars, I don't know. Then I'm too old maybe. Okay, thank you very much. And if there are any questions.
Also, you have all these qualification certifications. Is this also did RIOT also get some certification?
As said before, so when we are doing qualification, nobody cares if something is working. This is so the qualification is only that you are not harming other experiment or the rocket launch or whatever. When we are talking about actual space missions, like on ESA level, where you need some software qualification, but I think this has not been done with RIOT so far. So we usually use RTEMS because this is qualified. Would be an initiative to say, because what we are right now doing is we are putting also RIOT on our CubeSat that we are building in our group, and but we don't have any regulations. That's it. So, but yeah.
Anyway, questions, comments.
Too much hard.
Last question. How long does the battery last for this batch?
That's a good question. So right now, 7 hours, 8 hours with, let's say continuous streaming. So then we have 7 hours more or less that we can continue stream. But we have, we are also implementing energy efficiency mechanisms. One big drawback that we are also working on is, the MCU, or let's say the BLE socket, is not a big issue. And also the MEMS are not a big issue. The FPGA is the biggest issue. So in terms of energy efficiency, this is a killer. But there we are also working on mechanisms to say, how can we improve here the energy efficiency over time, which is also part of one of our projects, while not having a lower fault tolerance. Because this is also something, fault tolerance, as you saw, when we have 2 sensors, then it's double the energy. So therefore, but now 7 hours, we hope that we can get it also for 24, which would be okay. But you can recharge it.
With regard to the fault tolerance on the FPGA, when there are permanent faults that are accumulated in the FPGA, can you reassign the gates that you're building in there to different locations to route around faults, like you would do with bad blocks on a hard disk?
Yes, you can do it. I know you can do it, and so that's also the reason why we are really into this FPGAs, because there's an entire open source tool chain. So this YOSIS. I guess most of you maybe heard about that one. And it's really cool because you can play around with everything now. So we can actually do this. We know when there's a location that where we have permanent faults, we can then also reallocate the stuff.
Okay. When you talk about the safety validations for the device, you mentioned that batteries are a no-go for most often and burn.
Yeah.
Is there like some special battery that you use, or how do you deal with that?
So it's not an absolute no-go. If you get also qualified batteries for space applications, but they are in a range, thousands of euros for sure, because they are tested on everything. For our case, it is pretty simple because we are just looking at the capacity of the battery. And if it is below a certain threshold, which is for our battery the case, then more or less nobody cares. So therefore, when we are talking about coin cells and stuff like this, that's okay. Because when such a small battery might explode or might irradiate some kind of gas or whatever, then it would not be harmful for the astronauts. So this is always the issue. So when you have bigger battery packs, then you have to make a qualification process for the entire batteries as well. And what means no-go, maybe that was too hard. That is for sure it's possible, but the effort is much higher. And for us, it's like coin cell. There are handbooks where you can say, oh, if it burns, then it's not that harmful. But recharging is an issue. So that is something also right now, for sure, we have the ability of recharge the device via USB. But that would be something that would be not possible. So therefore, the question with the energy efficiency is pretty relevant. Or we make the qualification process actually for recharging. Let's see.
Regarding going back to the TA, permanent faults, I mean, do you implement or think of implementing some sort of monitoring, so where you can actually be measuring, for instance, the changes in threshold voltage while you're running, like periodically or so, to prevent for the incorrect space?
Yeah, exactly. So this is also what you are doing. So you're monitoring the power, and you see the different effects, like latch up. When you have a latch up, then you see a huge spike, because there's now a short on our devices, and it's easy to solve. You just have to reboot. You have to just cut off the voltage and then just reboot the entire device. So there you resolve the latch ups. For the total ionizing dose, this is something you cannot repair, but you can monitor over time. You can see, okay, there's a change also in the power consumption, and you see, when something is maybe on a tipping point, when it breaks. But it's exactly what you said. So that's what you do.
Christian?
You talked about radiation and all the kind of harm. Is it how likely or how possible is to simulate more or less the situation out there?
That's what we have to do when we are talking about this radiation testing. So here. So there are facilities where you can, let's say, simulate the radiation environment by having a particle accelerator. And the issue is always what kind of particle are we talking about? So if it's electron, you can also sneak into a hospital, for instance, and just do your radiation testing there. Actually, that was in a hospital. Or there are also radiation facilities which are selling this as a service. That you can go there and you can make, in this case, your proton testing. It gets really expensive when you go for ions. Then it gets really expensive when you have ion testings. And however, we are not more or less simulating the real environment, but we are also accelerating this a bit. So when we talk about LEO orbit, for instance, the dose rate that you have in a LEO orbit is, let's say, when you talk about a minute, it's pretty low. Maybe you have some bit flips in a day or maybe in 2 days. But what we are doing is we are just increasing here the dose rate to just shorten the time until you see effects. So we are simulating this, but like a simulation, we accelerate. This is not real time. So that's what I do. But this is what you do, which is expensive.
Following up on what you said on recharging batteries.
Yeah.
How about hybrid capacitors? Are they an option in space?
Yeah, I mean, the capacity is not that high, but good question. I never thought about this. If they are a huge, so usually in let's say in satellite structures, no, there's nothing like this for sure. But maybe for wearables, would be a good question. Yeah, have to think about this.
So there are no more questions. We thank you again. We learned a lot about things we never expected.
That's good. And if there are any questions, so don't hesitate to ask during the coffee break, because as I said, a lot of other things going on there.
Actually, lunch break.
Yeah, and have a good lunch.